I will just give you a brief introduction about the ESA Science Programme. We divide it into the solar system on one hand, and then you will see another chart for astrophysics. And in each of these charts, we have the legacy missions that have already done their work. We have the missions which are currently in orbit and working, and we have the missions that are in preparation for the future. And here you see the solar system lined up with the planets, and you see that most of our missions are actually currently in the inner solar system, in particular Bepi-Colombo, Solar Orbiter, new missions that are providing a lot of excitement. And let me just quickly give you some highlights. So for instance, Solar Orbiter, the first light has been published in July, and we have found something completely unexpected in these very high-resolution images of the sun. We have seen these so-called campfires, which have never been seen before, which may very well be responsible for heating up the solar corona in the quiet sun, which nobody understood how the corona is heated up when there are not these huge flares. We have Solar Orbiter together with several of the other missions working together. So it is a kind of orchestra which is working in the heliospheric in situ measurements. We have Solar Orbiter, we have Cluster, but we also have Bepi-Colombo that is running around in the inner solar system to try to reach Mercury. And all of them measure together the plasma and the magnetic field simultaneously, and this is a very exciting moment in time. There's one very nice paper that came out which lets us understand the Aurora better. You know, the Aurora is this northern lights and southern lights. It's usually a ring around the North Pole, but every once in a while it's breaking up. It is producing so-called substorms. And now there's a new study out which is actually using many different spacecrafts, including our cluster spacecrafts, that is more understanding how these substorms are created. They are created from plasma that is coming downstream from behind the Earth in the tail, in the magnetotail. There's reconnection, there's energetic processes happening, and then the stuff is flowing back to Earth and is finally hitting the pole and is destroying the Aurora. And something other, this is also very interesting for a future mission that we are proposing and that we are actually building together with our Chinese colleagues. It's a China ESA cooperation, which is studying the corona, it's studying the northern lights continuously. Something else about the corona, something unexpected. You know, the beautiful rubber duck comet, Churyumov-Gerasimenko, that has been studied by Rosetta. And we have now, by analyzing all the data, realized that the comet itself has an aurora itself. So there is actually particles from the solar wind that are impinging on the halo of the comet. Electrons are splitting up hydrogen, hydrogen from the water molecules. The hydrogen is ionized and is then recombining and producing this pink glow around the comet. Many years ago, we have already realized that comets also have an X-ray emission. So this is quite exciting. And then let me come to the nearby rocky planets. We have two missions working on Mars. And here is Mars Express that has actually caused quite some excitement a few years ago because it has found water under the pole, under the 1 kilometer thick ice layers of the pole, of the South Pole. And this study has been extended. And just a few weeks ago, this new map has been published, where now actually you see not just one water lake, but it is surrounded by some other liquid water in the South Pole region of Mars. It is very difficult to get through this 1 kilometer ice pack, but nevertheless, it's really exciting to know that there's liquid water on Mars. And then just last week, we had Bepi-Colombo flying by Venus before it was flying by Earth. This was the first Venus flyby, and another Venus flyby will happen in August. And these flybys are always a great opportunity to study the atmosphere and also the surrounding, the magnetosphere of these planets up close. And I just want to show you a little Twitter feed where one of our colleagues, Mark, one of our colleagues has added some atmosphere to Venus also. Venus has already a lot of atmosphere, but this is the musical atmosphere. Okay, that brings me to the solar system, to the astrophysics fleet. Again, we have a very large number of missions in the legacy archive, which we are dealing with at ESA, where all the legacy data are stored. And then we have the missions in orbit and also, again, missions in preparation. And there's one new mission, Cheops, which has added to our richness of possibilities. And I can give you a very first highlight of Cheops. I will also show you some highlights from Hubble and one from Maximum Newton. And so here, this is the first science paper that came out of the Cheops mission. And it is a very exciting system. It's a very hot star, much hotter than the sun. And the planet is about the Jupiter size, but it is 20 times closer to its star than the Earth is to our sun. So it is well within the Mercury orbit. And the Jupiter is basically tidally locked in this system. So it always looks with the same face to its star. On one side, it's very hot. On the other side, it's a bit cooler. And for the first time, I think it was possible to actually see the eclipse of the planet when the planet goes behind the star. So this is very rare. The planet has to radiate quite brightly. And you see here, also the data is quite noisy, but you see a clear eclipse. And then on the other hand, you also see the so-called transit, when the planet moves in front of the stellar surface. And that is this dip here. And when you look at the dip in detail, then you see that it is asymmetric. It is a little bit higher here on this side than on that side. And that is due to the fact that the star is actually gravitationally darkened. It is rotating quite fast in this direction. It is hotter in the pole region than in the equator region. And the planet is actually moving almost perpendicular to the rotation phase of the star. And so you can learn a lot of details with just these simple transition measurements that Cheops is doing. And this is giving very good perspective for the future. Now let me come to a very exciting field of dark matter, which I have spent a lot also in the recent years and months to try to understand better. This is a picture from the Hubble Space Telescope of one of the frontier fields, which is focused on some of the largest clusters of galaxies. And we are using these clusters as lenses, which are basically amplifying the galaxies behind the cluster. And what you see here, these fascinating ring-like structures, are the gravitationally lensed pictures of galaxies which are behind the cluster. The strong lensing feature, you can, in principle, this can be interpreted as an Einstein ring. You can then calculate the amount of dark matter that is necessary to create that Einstein ring. And this is a very strong piece of information about dark matter. Now, the new thing is that Hubble has found that the Einstein rings are not only existing in the cluster as a whole, but actually all of the bigger galaxies have their own Einstein rings. So here you see a blue galaxy, which is kind of circled around. Here you see a red galaxy with several images around this galaxy. And here you see these blue galaxies as well. And so when you then calculate the amount of dark matter that is necessary to create these structures, you come to the conclusion that every galaxy has its own little dark matter halo. So here you see the light from the galaxies in yellow and red. And the blue is actually the dark matter that is necessary to create these Einstein rings. And when we take out the galaxies themselves, the light, then only the dark matter is remaining. And you see that the dark matter is actually highly structured, much more structured than what is expected from the normal cold dark matter scenario, where you would expect a smooth distribution. And this is actually consistent, for instance, with the model that the dark matter is actually not made out of a single sort of particles, but it has actually different particles with different masses. And the small particles are actually congregating around the big particles. And this is what you expect if the dark matter is made out of black holes and not of WIMPs or axions or something like that. And this is actually amplified by recent measurements. This is not from the ESA Science Programme, but it is leading into the exciting LISA mission, the mergers of black holes that LIGO and Virgo is finding. And it turns out that LIGO and Virgo has found black holes of very large masses, but now they also have found a black hole which is only about 3 solar masses and should actually not exist. And like Ogle and Gaia have also found black holes which are in this region that are not allowed to exist. And recently, LIGO has found a monster merger of 2 black holes of about 80 solar masses into 160 solar mass. So as I say, the plot is thickening, and people believe that the LIGO black holes could also in principle be primordial black holes that are coming directly out of the Big Bang and not have been created by stellar explosions. And so we have also Hubble helps us there, because Hubble has recently identified the very good case of an intermediate mass black hole, a black hole of about 100,000 solar masses. And this was actually found by an XMM Newton and Chandra result where we see so-called tidal capture events, where a poor little star is getting too close to the black hole in the center, is ripped apart, is accreted, and there's a big splash of X-ray emission. And Hubble has then looked at where this object lies, and it turns out that the X-ray source is actually in a globular cluster, but not in our own galaxy, but in a globular cluster of another galaxy. And with this localization, Hubble could actually then identify this as a 100,000 solar mass or 10 to the 4 solar mass black hole, which is sitting in the middle of this globular cluster. And so we are now seeing a wide spectrum of black hole masses, much wider than we originally anticipated. And I cannot go into great detail, but I have recently worked myself on a theoretical paper where basically all the dark matter is explained by black holes of different masses. And there are several measurements also with ESA involvement, which is actually amplifying this result. And so it's a new speculation, but a very exciting possibility that the black holes that are created in the early universe are producing the dark matter. With this, I would like to finish. We are looking forward to a very exciting future. We are currently preparing the next 25 years of space science in ESA after LISA and Athena have been launched. And these teams are working, and we are expecting towards the end of the year what the next 25 years will look like. And with this, I would like to thank you and wish you all the best for the teacher training workshop.